Alright, today I'll be going over practice exams for the exam 2 AC power. So I'll be going over spring 2019 and fall 2019 exams. I just picked those randomly. So this number 1 is asking us to find ZL for maximum average power transfer and maximum average power. Alright, so to calculate average power, first we need to find Thevenin's equivalent, and then we will find maximum average power transfer. Okay, so for VTH, so when you disconnect this load from the system, there'll be zero current flowing this way, so the only current would be flowing around here, and your VTH is simply just going to be the voltage drop from this 3 ohm resistor. So simply VTH is going to be equal to, it's going to be 4 phase angle 0 times 3 ohms. It's going to give you 12 with phase angle 0 volts RMS, since this value is in RMS. All right. And now we want to find is ZTH, so the equivalent resistance with respect to ZL. So to do that, we simply just have to turn off this current source. So you'll have open circuit, and then you'll have this resistor and the inductor. And what you want to go is from point A, so we're going to start at point A and end up at B. We're going to go from A, we're going to go through this inductor and then through this resistor, so they are in series. So ZTH is going to be equal to 3 ohms plus 4J ohms. All right, but since our load is complex, our Z of L is simply just going to equal the conjugate of ZTH. So 3 minus 4J ohms. All right, to calculate P max, it's simply just going to be the magnitude of VTH squared all over 4 times RTH. Since this is in VRMS, we don't have to have that factor of 1/2. So VTH squared is just simply going to be 144, because VTH was 12 phase angle 0, all over 4 times RTH. It's not going to be ZL, it's just going to be RTH, so that's just going to be equal to 3. So times 3. So now this is going to be equal to 144 over 12. So simply our maximum average power transfer is going to be 12 watts. And that's it for this question. It's pretty simple. Yeah. Now I'll move on to problem 2. This is going to be pretty simple. So we have this 10 with a phase angle of 0 amp RMS current source. Then we have this 20 ohm resistor with a current flowing through it, and we have this unknown load. All right, so the problem asks us for the given circuit where I, for this current, is equal to 4 with a phase angle of 35 degrees amp RMS, find, for the first part is to find power P absorbed by the 20 ohm resistor. Okay, and that's going to be pretty simple. We're just going to use the equation P of 20 ohms is going to be equal to the magnitude of the current flowing through it squared times the resistance of the resistor. So that's going to be simply going to be 4 squared times 20, which is equal to 320 watts. Oops. All right, now the second part is asking us to find the voltage applied to the load. The voltage applied to the load is going to be pretty simple. Since this resistor is in parallel with the load, the voltage across the resistor is going to be the same voltage across the load. So I'm going to say VL, the voltage of the load, is going to be equal to V of the resistor, of the 20 ohm resistor. And that's simply just going to be equal to the current, which is 4 phase angle 35 times the resistance, 20. And that's equal to 80 with a phase angle of 35 degrees. And that unit is volts, RMS. All right, now is asking us for the total apparent power, S, of the source, and the active power supplied by the current source. Okay, so to do that, it's simply just going to be the voltage across the, it's going to be the voltage supplied, which we already know that is going to be 80 with the phase angle 35, times the current, which you already know, times the current, the complex conjugate of the current, which is going to be 10. So C, we're finding the complex power is going to be equal to, it's going to be 80 with the phase angle of 35 times the conjugate of 10, the phase angle of 0. The complex conjugate of phase angle of 0 is going to be 0. So this is just going to be simply equal to 800 with a phase angle of 35 degrees. So now to find the apparent power, which is going to just be equal to, S would be equal to the magnitude of the complex power, and that's just going to be your number in the polar form. So this will be equal to 800 VA. This is also in VA, or volt ampere. Okay. Now to find the power supplied is going to be P of the source, and that's just going to be the real part of 835, which is equal to 335.32 watts. Ask us find the active power P absorbed by the load. So with that, we can just use the conservation of complex power. So with that instead, so SL, or the complex power across the load, is going to be equal to the complex power of the source minus the complex power of the resistor. All right, so that's simply going to be equal to $800 with a phase angle of 35 minus 320 with a phase angle of 0. How did I get this 300 with a phase angle of 0? Since it is a resistor, it is purely resistive, so that means that the only thing that accounts for its complex power is its average power, which is 320 watts. So I just put that in. And since it's a resistor, it has a 0 phase angle. All right, so now with that, just do some stuff in your calculator, and you will find this is equal to 568.32 with a phase angle of 500 no, not 500, 53.84 degrees. And this is all in VA. All right, and just like with C, to find the apparent power of the complex power is just going to be the magnitude of the complex power. So it's going to be equal to 568.32 VA. And, in order to find power, or the apparent power of the load, it's going to be equal to the real part of the complex power, which this is all equal to 335.32. And I just noticed I was looking at the wrong value for our source power, and that's going to be equal to 655.32 watts. And you probably could have just done your power of your source minus the power of your resistor in order to get the power of the load as well. There's just different way of looking at it. I'll write that down. So we can do PL is equal to P the source minus P of the resistor 20. Just a different way to do it. Finally, this is finally asking us of the power factor of the load. So E power factor is going to be equal to PF of L. It's simply going to be equal to cosine of this angle right here, which is going the angle is the difference of voltage angle and the current angle. So 35 minus 0 is equal to 53.84. So it's going to be equal. So power factor of the load is cosine times 53.84, and this is going to be equal to 0.59. And since our angle is positive, it is lagging. Boom. This question is all done. This practice test I think I found was the easiest one. So don't expect the exam to probably be like this, but just to kind of understand what all these numbers can come from, yeah, that's why I did it. We are now off on fall 2019 practice test. So this is problem 1. It's going to be another maximum average power transfer problem. Just a note that the source is not in RMS. So that will only matter at the end of the problem, but might as well point it out now. All right, so now what we need to do is find VTH and ZTH. So VTH is pretty simple. When this load or this resistor is pulled out or disconnected, there'll be no current flowing through here, so there's no voltage through this resistor. So the only voltage, the VTH, is simply going to be the voltage across this inductor. So to do that, we can just do simple voltage division. So we have our current voltage source is going to be 10 with the phase angle 0 times the value of this inductor, which is going to be J15 over J15 minus J20. And that'll come out to be negative 30 volts. Okay. And now ZTH is pretty simple as well. So when you find that, make sure you turn off the source. So you have something that looks like this. Okay. So ZTH is pretty simple. You're going to see that this 10 ohm resistor is going to be in series with these two parallel components. So it's going to be equal to I can just write it like this. plus J15 in parallel with negative 20J. And this will result in getting 60.83 with a phase angle of 80.53 degrees ohms. All right, and the last thing for this is that since this is a variable resistor, that means it can't be complex or it can have reactance. So that means we use the equation RL is going to be equal to the magnitude of ZTH. So it should be equal to 60.83 ohms. Now the problem asks us to find the maximum average power delivered to this resistor. So we'll do that. We're going to redraw the circuit with Thevenin's equivalent. So we'll have our voltage source that is going to be negative 30 volts. That is going to be with a load that's going to be equal to this. So it's going to be 60.83 then 80.53 degrees. And all of that will be, and in series with that will be a resistor, which is equal to 60.83 ohms. All right, so what we want to do is find Pmax. I'll write this over here. Pmax of RL is going to be equal to 1/2. Remember the 1/2 because our value is not in RMS, so it's in peak form. It's going to be 1/2 times the current flowing through it squared times the resistance. All right. So what we need to find is this current, because we already have the resistance, which is 60.83, and we know what 1/2 is. So the current is simply going to be equal to, using Ohm's law, negative 30 over 60.83 plus 60.83 with 80.53, which is equal to 0.32 with a phase angle of 139.7 degrees. So now we have everything we need in order to find Pmax. So it's simply going to be equal to 1/2 times 0.32 squared times 60.83. And this will give you 3.11 watts. Boom. Done our third problem, our first problem of practice test 2. All right, our final problem is a power factor correction problem with a little bit of annoying things. This is the last problem of fall 2019 practice exam. All right, so let's get started. So first, part A asks us to find IS, so the current coming out of the source. To do that, it's a little complicated because we need to find the voltage coming out of, we need to find the voltage across this in order so we can find the current flowing through that. Do that, we need to do some pesky some pesky nodal analysis, which everybody loves. So nodal analysis, make this Vx. And since this is going to be a voltage source that is nothing else is in series with it, or is directly connected to ground, then this is equal to just 50. And then this node is simply 2Vx. All right. So KCL at Vx, or this point in the middle, we're going to go from Vx to 2Vx through this negative J4 capacitor. So it's Vx minus 2Vx over negative J4. Then we're going to go from this Vx to ground, which is going to be Vx over 3 ohms. And now finally, go this Vx to this 50 volt current or voltage source. So Vx minus 50, phase angle is 0, all over. Then we went through this J6 inductor. So 6J. And now, with some fun, oh yeah, this is all equal to 0. So now, this is going to be equal to negative Vx over negative J4 plus Vx over 3 plus Vx over J6 minus 50, phase angle is 0, J6 is equal to 0. So I'm going to move this over to the other side and factor out Vx from all of this. So we'll have Vx times 1 over J4 plus 1 over 3 plus 1 over J6. And this is all going to equal 50 over J6. And now you simply just divide this by this, and you'll get Vx is equal to 39.04 with a phase angle of 14.47 degrees volts. With Vx, we can now finally solve for Is. So to find Is, this is part A, is going to be equal to, the current flowing through here. So it's going to be 50 minus Vx all over J6. Because we're starting here, ending up here, because our current is going from left to right. So then this is going to be equal to Vx, you just plug in Vx right here, and you get 6.51 with a phase angle of negative 75.5 degrees amps, RMS. Now, part B is asking us to find the complex power of the voltage source that's independent, or the independent voltage source. So S is simply we have the voltage and now we have the current, so we just do the voltage times the current. But make sure you do the complex conjugate of the current. So this is going to be equal to 50, phase angle is 0, times 6.51. The phase angle of the complex conjugate of this is just going to be 75.5 degrees. And now finally, our complex power of the voltage, or the current voltage source, keep on mixing those up, is 325 with a phase angle of 75.5 degrees. Boom, done that part. Now part C asks us to find the power factor of the independent source. So PF is simply going to be equal to cosine of theta Z, which is going to be voltage minus current, which is already this, so it's 75.5 is equal to cosine of 75.5, which is all equal to 0.25 lagging. Now this problem is asking us to add a reactive element that will make the power factor correct to 0.95. So part D, we want PF equal to 0.95. And in order to get our theta nu, it's just simply going to be equal to cosine inverse of 0.95, and this is equal to 18.15 degrees. And our theta old is equal to 75.5. So it asks you to add a reactive element, so that you could add a capacitor or inductor from A to B. It doesn't really matter which one you add. I chose to add a capacitor because that's what you usually do in all cases with power factor correction. All right. So the value of the capacitor is going to be C, the capacitance, is going to equal to the real part, or that's going to equal to P here. I'll write the whole equation now because it's kind of important. The average power of the old times tangent theta old minus tangent theta new all over 2 pi f, the frequency, times the magnitude of voltage RMS squared. All right. So to get P old, we simply just do the real part of our complex power we calculated back in part B. So it's going to be the real part of 325, it's 325, and then it's going to be times tangent of the old is going to be 75.5 minus tangent of 18.19. This is all going to be over 2 pi times the frequency, which was stated in the problem to be 50 hertz. So it's times 50 times the VRMS squared, which VRMS is going to be equal to 50 phase angle of 0. So it's just going to be 50 squared. And this all comes out to be 366.3 microfarads and capacitor. All right, so the last part of this question is to calculate IS of the new power factor, of the new capacitor put into this circuit. So new IS. Okay. So first we need to do is calculate the new complex power of our source. So since we only added a reactive element in, the only thing that should change is the reactance of our complex power. So complex power of new is going to be equal to our power of old plus Q, that's theta, wrong symbol, Q new. So this can be equal to real of 325 with a phase angle of 75.5 plus Q new. Okay. Now we have to go to the power triangle. So we have triangle like this. We have Q, P, S complex, and then we have theta. in order to get our new Q, we have the power, because it stayed the same, and we have theta, which was 18.19. So in order to get Q and P, they're related by tangent. So Q is going to be equal to, or Q over P is equal to tangent theta nu. So that means Q is going to be equal to tangent of nu times P. So tangent of 18.19 times the real part of this is actually equal to 81.5. Yes. So this is equal to 26.71 VAR. So now we can finally get our new complex source is going to be equal to 81.5 plus 26.71 VA. We are not done yet. We just calculated the new complex power, but now what we need to do is calculate the current. So using the formula, IS is going to be equal to the complex power divided by the voltage, which is 50, phase angle is 0, all of that conjugated. So now you plug in S nu for your complex number and 50, you get 1.72 with a phase angle of negative 18.19 degrees amps. All right, so that is this question done. It's a long question, and it's a little tricky because especially when you look at this question, you see this dependent source, you think, oh crap, I gotta do Thevenin's with this. But you didn't have to do Thevenin's, you just had to do nodal analysis. Good luck on the exam too, and I hope you all do well.